All right, this is the second video for the review of the second test for rational functions. Again, really confusing as far as the title, but what we're going to be looking at in this one is the graphing of the more complex rational functions and also the solving inequalities with the rational expressions and all. All right, the very first thing you should do with any of these is go ahead and factor them. I did factor out a GCF at the beginning here for the top and then completely factor the bottom. Once that GCF was out, I was able to identify that I had the difference of squares and completely end up factoring it here. Once you have it factored, these are the general things that you're going to go through, and they should help you put together a graph for it. Number one, I'm going to look for holes, and two, look for asymptotes. That stuff really comes from the same place, but if you have any holes, you really want to identify that those things are there. All right, a hole is going to happen whenever you have a factor in the numerator and the denominator, which is occurring right here. So as you're getting ready to graph it, you're going to want to have that canceled out because you don't really want to look at it anymore. But you do want to acknowledge that you do have a hole. So that we are going to have one at x equals 1. And that ends up being the very last thing that you're going to come back to when you finish up your graph. So you need to maybe write a note or something that's just going to remind you, like, look, come back and do this at the very, very end of this whole thing. You could add it to the end of the list if you want, just a duplicate maybe to remember. All right, vertical asymptotes, those are going to be anything that make the bottom equal to 0 that we wouldn't have already canceled out. So that's going to be at x equals -3. And you should probably graph as you go. All right, so the vertical asymptote that we do have is at -3. In the instructions, it's going to say to use a dashed line for these, but since I'm using two different colors and for the video's sake, I'll do that as a solid. But it does tell you exactly everything to do. So you got our vertical asymptotes dashed. I'm now going to move into the horizontal asymptote. That is based off of comparison of the degrees from the top and the bottom, which you might be able to see a little bit easier in the standard form, but it's still there in the factored. You do have up to an x squared in the top, and you have an x squared in the bottom. So they're equal in degree, and when that happens, your horizontal asymptote is going to be when you reduce the leading coefficients. So we don't look at these three things at all. We just divide the 2x squared by the x squared, and you get 2. So that reduces down and gives you your horizontal asymptote here. Okay, so now we've got 4 distinct sections for this one, which will be all of your little areas that you can graph in. All right, so that was technically at y equals 2. The y-intercept, that is going to be plugging in zeros for your x's. Again, standard form might be the easier spot to get that one from, but you can still do it in this one that's here. So if I did plug in a 0 into the standard form, anything with an x will just go away and you get -2 over -3, which means that the y-intercept is going to be at 2/3. That you can also get from here because you'll have the 2 times 1, which will be the 2, and there's your 3 in that. All right, so y-intercept at, what was it, at positive 2/3 is going to be about here. So it doesn't need to be perfect, but we do need to see the dot. So we're going to have asymptotes, we're going to have holes. The intercepts are going to be closed circles that we really want to be obvious that we're seeing them. So there's 1. Again, it doesn't have to be exactly at 2/3, but you know, between 0 and 1 is fine. All right, well, I won't write down that coordinate. You saw where it was. The x-intercept is going to be anything that makes the top equal to 0. Okay, so I go back to, not to this one, because you really want to see this now in the factored form. I'm going to go over here, and again, not looking at that because it's a hole. The only thing that gives you a 0 in the numerator here is going to be a -1. So that's going to be right there. And once those 2 points are plotted, you really get a sense that everything's working out well. Because then we can sort of see that curvature in the graph over here. And those 2 points are near each other and they're in the same area, that it seems to fit nicely, that it gives you that shape. All right, so as far as the rest of the graph, look, we don't have any other intercepts. They don't exist, so you can't plot any points over here. You don't really need to have any real true coordinates for it, so we're not going to ask for any more from there. The rest is really just kind of figure out where the graph's supposed to be. We do not have togetherness because we don't have a double factor in the bottom, and we also don't have any more x-intercepts, so the graph can't exist over here. So our result will be that it's sitting over in that area. It doesn't have to be a perfect sketch, but it should look like it's going along those asymptotes, so I could probably do better on that end. But it should be matching up to the asymptotes and then having that sort of curved shape as it comes out of it. So that's a little bit better. All right, and last, that hole, which was at x equals 1, we're now just going to go back to the graph and find out, like, wherever x is 1, just match it up to your graph, take out that spot, and show us an open hole. Now, it is possible to get the true height from that one, and the way you do that is you take that 1 and you plug it into the function where you've already got this canceled out, so it's not undefined. So if I were to plug that 1 in there, this is going to give me 2 times 2, which will be 4, and those will give me 4. So it should be at a height of 1. We actually end up figuring out that it's also at 1. And luckily, my dot ended up right on that spot. But we definitely want to see it lined up with like where that x would be. All right, the second graph. Already got that one factored out for us as well. So this one maybe will go a little bit quicker. Holes. We don't have any common factors in the top, so just nothing there. Vertical asymptotes are going to be at -3 and also at +2. So we're going to end up getting 6 regions for this guy. The horizontal asymptote is, well, when you look at the comparison of the degrees, you got a 2 versus 1. So if you're degree heavy in the bottom, you're automatically going to be at the x-axis. So this is going to give you a total of 6 regions. The y-intercepts and the x-intercepts are going to help us figure out where those are at. The y-intercepts, when you plug in 0 for all your x's, looks like, well, because if you got a 0 on the top there, then that's going to make the whole thing 0. So it's right in that spot. Okay, and this is always the point that I really don't like getting as part of my graph, because if you knew that you were above or below like the asymptote, then you can kind of figure out where the rest of all this stuff is going here. Let's see, no other x-intercepts, no other y-intercepts. Okay, things that we know for sure though is we don't have any tangency. We don't have any tangency because that's not squared, so it's not going to be bouncing off of this in that spot. So it's going to be sort of like S-shaping through there in one way or the other. The other thing that we don't have is any togetherness because you don't have any double factors that are in the bottom. Okay, so what I would probably do in this case is just choose a value to see roughly what region that we show up in. Okay, so if I chose a number that was just somewhere out here, like I chose a 6, and I plugged that in, I would get a 6 over, let's see, 9 times 4. That's plugging the 6. And the most important thing that I take out of this is that all of that turns out to be positive. So that means that my graph is going to have to be up in this region. Okay? And once I've got that set, and I know that I don't have any togetherness that's happening down here, I didn't have any double factors in the bottom, then I know I can't draw the asymptote here. And no tangency, so one thought would have been kind of going through in that area, but since I can't do that, I'm going to need to come from the bottom and make it look like this. That way I don't have the togetherness. I do pass through that point, not turning around on it. Then I also got to then gravitate towards that other asymptote. And since this asymptote doesn't have togetherness, then the only place the rest of it could be is here. So this is an unusual case where the intercepts didn't actually give you like a quadrant or an area to really set up and start graphing, and I just made up another test value. But once I had that, the rest of it could be built based on the things that we knew. All right, last, solving the inequalities. Most of the work I've already done here, just so you wouldn't have to watch me move stuff around, but the very beginning is to make sure that you have it set equal to a 0, or the inequality one side's a 0. So I did look at the 5 minus x as a single item. That moved over through subtraction. So that's what everything in the blue is here. I just have the minus, and then I kept that as a single item. But in the next step, you're going to have a common denominator. So I went ahead and already had it over the fraction bar and just kind of bubbled up in there. The common denominator is going to be whatever this one has as that denominator. So I made sure to multiply the top and the bottom by an x. Okay, and then after doing those things, There's my 3x minus 15 from that. The minus is going to go to the 5 and the x, so you get minus 5x. This is going to be a negative x squared, but with that negative becomes a positive x squared. Everything over x. You're going to regroup. Once you have it all cleaned up here, check to see if it factors out. It's quadratic. We probably have it designed so that it does. If it's not a quadratic, it's just going to be a little bit of an easier problem. Factor if you need to, and it gets us to this place. Once you get to something like this, where you don't have any standard form stuff going on, anything that can be factored needs to be factored. From here, what we do is we pick out what we call critical numbers. The critical numbers are anything that make the top equal to 0 or the bottom equal to the 0. So on the bottom, it is going to be at 0. And that is a vertical asymptote. Okay, kind of keep that in mind. In the top, it's going to be at a positive 5. It's also going to be at a negative 3. Now these are going to be roots, so things that make the top equal to 0 are roots, and we already knew that from the graphing and X intercepts. And the important thing about understanding these as roots is that these are places that actually contact the x-axis. Okay, and when we've got all this set up as less than or equal to 0, remember that we're doing that because we want to find where the graph is greater than or above the x-axis, and also when it's less than the x-axis. But if you have an equal to version here, okay, then the roots are going to be included, so they're not really boundaries. So as of right now, here's all the intervals that do exist for this problem. I've got negative infinity to negative 3 with a bracket because it's on the x-axis. I've got negative 3 to 0. That's going to be a parentheses because it's an asymptote. It doesn't actually reach, well, this is an x-intercept anyway, but you know how asymptotes work and you don't actually end up there. The next interval is going to be 0 to 5. 5 is also going to be a bracket. That's a root. And again, roots are only brackets if it's the equal to. If it didn't have the little bar under, then it's all parentheses across the board. Okay, so then there's 5 and then goes on to infinity. And then what we do from here is so these are your answer choices. It's like an A, B, C, D kind of thing you got, and you can have as many or as few, like actually that work here. What we do is run some test values. We plug in some numbers into this thing over here and see if we get positive or negative. Okay, so if I plug in a negative 4, into this, I'm going to get a negative 9 and a negative 1. So I get negative negative over negative 4. Okay, that's going to become positive over negative. So all that is negative. Now if I plug in negative 2, that's going to give me a negative 7. So a negative. But negative 2 plus 3 is a positive. And my negative on the bottom is negative. These will cancel, and I end up with a positive. I then test something like a 1. And I plug in the 1, I'm going to get a negative when you subtract. I'm going to get a positive when I add on the 3. But the bottom will also be a positive now. So I'm getting 1 negative out of all of that. That means negative. Then last, choose something larger like a 6. 6 minus 5 is a positive. 6 plus 3 is a positive. 6 on the bottom is positive. Everything's positive, so there you are. And now, in conclusion, to choose what intervals you're going to keep, you go back to the inequality, and this one said that we want it to be less than or equal to 0. So we want those negative intervals. We don't want the positive ones. Okay, so we're going to keep the negative infinity to negative 3 with a bracket. That's the negative one there, and then we're going to skip over, and we're going to include the 0 to 5. In other words, when all this is graphed, these will be the areas that are sitting above the x-axis or in contact with it, and then, below, because we want negative. And these will be the ones that are above, and that's not part of the solution set that we want. Independently, if you want to go ahead and graph this, or even graph like way back at the beginning parts here, and see how the graph does, in fact, match up to that.